Hi guys, welcome back to the channel. In this episode I'm going to show you the plan, what we have to do to design this memory controller. And it's good to have a plan because that shows that we actually understood what needs to be done and we understood how the memory works from the datasheet. So let me know in the comments if it's too fast or it's unclear or whatever. Hi guys, welcome back to the presentation. So I'm going to show like 100 miles per hour what's the plan to design this controller. This is my second take because I realized that some things that were not visible in the presentation, so I'll try to be fast as I can. So first we need to define the ports. We need to define the ports because we are going to generate a test bench, so we need to have like a black box with all the ports coming in and going out. Now, I'll show the internal architecture, what's inside the controller, and I'll mention a little bit about testing, not much. So probably that testing will leak into the next episode. Okay, so on the memory side, we have the clock going out to the memory, which is shifted 90 degrees. I'll explain later on why. Chip select, reset, DQSM signals, which are SDR. Now the DQSM is bidirectional because we need to read the DQSM to figure out if there is a collision at the beginning of the transaction, and then can become an input or an output depending on the type of access. Now the SDIO, obviously they are bidirectional and they are DDR. Now on the computer, I say computer side, but actually on the FPGA side, not internal into the FPGAs, we have the clock. This is different from the clock which comes out, different as in phase because it's the same clock. But it's the let's say zero phase clock or the normal clock. Then we have the address inputs. I kept 32 bits just to have it generalized if we want to, in the future, to support different sizes of memory. The data part internally, I kept it to the 8-bit, but we might expand in the future. I separated the data in with data out completely inside because there is no point to be combined. Now, important signals are the write not read, which tells the controller this is a read access or a write access. Enable, which is a qualifier which stores the command saying this is what we want, take the address and the data if it's about the write access. The register enable, tells the controller I don't want to access the memory array, I want to write or read from the register. So basically there are three important signals which they define what we want to the memory. It's the read not write, enable, and reg n. Now we have a busy output. Busy means that when we issue a command to the controller, it will raise the busy output to let us know, don't give me another command because I'm busy doing something here. So if you send me a command, it's going to be ignored. Okay, this is a graphical representation of what I just said. So those are the inputs, the clock. This is the clock going out to the memory, shifted by 90 degrees, so time shifted or phase shifted. Then we have the chip select. Then we said those are the signals which they go to the memory, and those are the signals on the FPGA side or on the internal side. The three signals which they define what we want to do: the read or not write, enable, and register access. Now the data parts in and out. Now we have another signal data out valid, which is going to tell the FPGA that what comes on the data out bus, it's valid. This is what it should be stored. And the busy signals, of course. This is simplified. We might have more signals. Okay, so how we produce the clock, the 90 degrees shifted clock. Everything starts with an oscillator, 100 megahertz oscillator. We use a DLL or a PLL to double this clock to 200 megs because that's our target, 200 megs. And then we generate this phase shifted, 90 degrees phase shifted clock. Why? Everything that we send out from the FPGA to the memory, so out from the controller going to the memory, the signals are going to change on the rising edge or falling edge of the clock. I'm talking about the SDIO signals. Because the other signals, they are going to change only on the rising edge. I'm talking chip select, reset, and others. But the data, the SIO signals, they are going to change here. They're going to transition on the rising edge or falling edge of the internal clock. Now, the memory is going to sample based on this clock, on the 90 degrees shifted, in the middle, away from those transitions, in the middle of the eye. So if you want to poke somebody in the eye, just poke it properly. So you take it here in the middle of the eye. Now, when the memory is going to send data to us, all those changes, they are going to be shifted based on this clock. So we need to sample on this clock. So everything FPGA is going to use this clock. Everything memory is going to use that clock. So, okay. Now we have a lock signal which shows when the PLL or DLL has achieved lock after a reset. Okay, next slide. For the I/O signals, which are DDR, I'm talking the SIO signals, we need to use special registers. Those are the DDR registers. So we present the data SDR, but it comes out of those registers as DDR. Same thing when we capture data coming from the memory, we use the input DDR registers. Those are resources which are on the I/O side. So they are very close to the I/Os because timing is critical. So we need to instantiate them as library blocks. Now, I think the tools are clever enough actually to instantiate those blocks if you write the code in a certain way, but I'll just instantiate them just to have control over things. Now, this is a simplified view on what's the I/O site. When I say site, the I/O actually has some logic attached to it. It's not just a pin. So this is the pad, which is the pin of the FPGA. And this is the output. The top side is the output path. So we have this ODDR register where we present the data, the D0 and the D1 as SDR signals. We present the clock. And here we are going to have DDR signal. Now, this bus, the SIO, we need to turn the bus from input to output depending on the operation that we are doing. When we write, is going to be an output. When we read, is going to be an input. So we have this tri-state buffer here that we need to drive when we make a write, and we need to isolate when we make a read. So when we make a read, this is going to isolate, and the data will flow here in the IDDR, which is going to capture the DDR data, and is going to present to us as SDR signal. Okay, next slide. What's inside the controller? Inside the controller is a state machine. What's a state machine is like an automata. It's like an automation which goes from one state to another, like a flow, right? So who's driving the state transition? So first of all is the clock. The clock is like the engine which is going to move the state machine. Now, based on those signals, the read, write, enable, and register enable will decide which way the state machine will flow. Because at the beginning, the flow is going to be linear. When we present the command and we issue the address, the row address and the column address. But after that, we need to do the decision depending on what we do. We write to register or we read or whatever. Okay, so of course, the state machine needs to generate some outputs. We need to generate the busy signal. We need to generate the proper driving of the bus. We need to figure out if DQSM, we read the DQSM or we write the DQSM because it's bidirectional. We need to drive the chip select, reset, and all other signals. Okay, so this is the representation of the state machine, right? State machine, we have those inputs which they move the state machine, and we have the outputs which they are decode based on the state we generate those signals. Okay, next. The next is actually very important. We assign state with meaningful names. Why meaningful names? Because we are going to simulate this, and we want in simulation to those states to be recognizable. So we don't call them state 1, state 2, state 3, and we are wondering, okay, well, what was state 3 doing? No, we put like meaningful names. You see here the command states. So first of all, we start from an idle. Idle means the controller is sitting there doing nothing, just being handsome. So that's the idle state. Now we transition from the idle state into command state when the enable signal comes with all other signals like read or read not write. Now, of course, based on those signals, we transition command 1, command 2. This is actually the diagram from the datasheet. And this is common regardless what we do with the memory, what kind of operation, this is common. So this part of the state flow of the states is going to be the same regardless of what we do. So from idle, we transition to command 1, command 2, so the first clock of the command, the second clock. Then the row address, we present the first clock of the row address, the second row, column address, column address. Now, from this point onwards, we branch. And how we branch? Well, we branch depending on what we need to do with the memory. And we have different flows here. Let's, for example, after we present the command, what we want to do, the row address, column address, if we want to write in a register, immediately we go into register write 1 and register write 2 states. Because the writes to the register, there are 16-bit accesses, so 2 clocks, and that's it. So it goes bang, 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 done. Now, when we want to read from a register, we have latency. So we go into this latency count state, and we sit there for a while, and then we read from the register if it's a read of the register access. Now, if it's a read or the write of the actual memory array, we transition into those states depending on the signals. Now, on the next slide, I showed here what are the signals which we take decisions based on. So, first of all, everything triggers if there is an enable. We latch a new command address and data and whatever all other signals. So, if enable is changing state from low to high or from 0 to 1, we know that we trigger the flow. So it will transition here in those states, and it will go bang, 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 bang. And here on the column address second cycle, based on if there is a register enable access, we go into the end, of course, if it's a read or write. We branch into this flow, or we branch into this flow, or we branch into this flow. So those are the signals here in green, which they are decision points in how the state machine is going to branch. Okay, next. We have this, let's say we figure out the flow. We have the states and it flows correctly. Based on the states that we are in, the present states, when the state machine is going to advance, we need to decode the output. So we are going to generate the chip select, reset, DQSM, data out valid, high Z. High Z is the signal which is going to turn the bus, in the SIO bus into output or input. Is that T buff from a previous slide? Of course, the busy signal, the moment we trigger the flow, we raise the busy and say, we don't take bets anymore until we finish, and then we lower the busy signal. Now, here is a new signal called error. It's a good practice to assign an error state and to capture all the possible funny transitions which they may happen with the state machine, and capture that into an error state and then back to idle, because it helps with the debugging. Now, next one. Now, what are the next steps? Well, obviously, write a test bench. So, a test bench which is going to instantiate, this is going to be in the next episode. I'm going to generate or write a test bench. I say generate because I might use AI. And this is where defining the input, output, and the whole controller as a black box will help. Now, write the test bench, write and test your state machine in simulation. So, we need to start coding the state machine. We need to define the states, which we just did. We need to, let's say, write all the states, or enumerate all the states that we want, and write the state machine. Then a very important step is harden your state machine. Harden the state machine is make sure it doesn't go in funny states, or it doesn't stay forever in a state if one of the transitioning signals. So you have those decision making points, and if one of those signals is missing or doesn't come, for example, in the case of a read, we are waiting for the DQSM. What if the DQSM doesn't come? We just sit there forever. So the state machine is going to be locked in the busy state? No. We need to make some sort of mechanism to get it out of that state if some signals is missing. Now, those are, let's say, nice to haves. Okay, so that's all I have. I hope you didn't fall asleep, and I hope it was useful. And I shall see you in the next one.